Okay, so I have some announcements. You already know homework 4, or last homework, is due on Thursday, and that's the cinematic UIs, so finding interesting examples of user interfaces in TV or movies. Exam 3 will be released on Thursday, and then it will be due Wednesday, which is the last day of class. And if you need some extra time on that, that's fine, but hopefully it will be pretty easy to get it done by Wednesday. But I do know that everybody's trying to study for finals and do a million projects, so flexible on that. Thursday will be our last day of class, I decided. We will go ahead and not meet on Tuesday, April 23rd. And that's mainly to give you time. If you want to spend that time working on the exam, you can do that. If you want to work on your project, you can do that. And if you would please complete the class climate course evaluation, which is finally online after years and years of paper. So I think you can find that. They probably sent you an email about it. You can also find it on Canvas. So you can use the time to do that if you'd like.
So when's the last presentation?
For our FedEx presentations, it is the 30th. So that's our final exam period. Tuesday, April 30th, 12 p.m. to 3 p.m. in here. And so that'll be our final presentations. Will be due then. And FedEx will actually be here for those. So they will not be connecting through the WebEx thing. They'll actually be here. So today we'll cover AI and machine learning in HCI. And then on Thursday, we will wrap up with a bunch of robots. VR and AR, I kind of moved that to be with the robots. And then we'll talk a little bit about ethics, and then just kind of a few other random things that people wanted to hear about. This is kind of the more fun part of HCI. But, so we won't have class on the 23rd, so that'll just be a work day.
Is the final exam scheduled on last day?
I think so. I usually just Google MS State Academic Calendar, and then it's usually first. But yeah, it should be posted. Okay, so last time we talked about social HCI and sad Mark Zuckerberg there. And social agents, social avatars, and why social HCI is an important thing, and why it's more and more something that we're looking at beyond just designing interfaces that are usable and efficient. It's kind of the social impacts that interfaces have, that systems have on people, and stretching beyond even, like the classic thought is, an interface or a system that facilitates social connections between people is obviously falls within social HCI. But then thinking more to things that people consider their own social agents. So a lot of these artificial agents, whether that's a robot or something like an Alexa in your home, or even just like Siri or Cortana or whoever, whatever voice assistant that might be on your device. So today we'll talk about what's kind of heavily rooted in that is AI and machine learning and how that relates to human-computer interaction. So we'll start by thinking about artificial intelligence, and I have a video to get us started.
More AI tools, deploying new AI tools, deploying new AI tools that we deployed or weren't AI tools. Build AI tools, building AI tools. We will have AI tools, sophisticated AI tools, AI systems. We will have AI tools. In general, I think over time we're going to move towards more proactive review with more AI tools.
Okay, so thought that was a fitting video to kind of kick this off. So that was Mark Zuckerberg in his latest, testimony before Congress about whatever Facebook was doing. But the solution that he was pushing was obviously AI tools, right? And what does that really even mean? Obviously, in Facebook's case, we're probably talking about content moderation of some sort. So how do we prevent fake news from spreading? How do we find automatically detect things that are not allowed on the platform? How do we regulate the platform in an automated way? In a way, because obviously we don't have enough people to do this, so we're going to kind of apply some type of automated algorithm or system to regulate the content. So we're going to talk about both artificial intelligence and machine learning. And right now, like today, pretty much these are kind of synonymous, and definitely we tend to focus on machine learning a lot more, like in the past 5 to 10 years. But talking about artificial intelligence, just to give you a kind of a quick summary of it, how many people have taken an AI course here? Or okay, so a couple of you. So this is kind of the book in terms of AI. So it's Artificial Intelligence, a Modern Approach. So if you want a good reference on just AI as a subject and kind of foundations of it, this is a great book to go to. So this is from that book, and this is just a table of 4 different things talking about what artificial intelligence is. I'm going to go ahead and kind of spoil it for you and just say that there's not really a clear-cut definition of what artificial intelligence is. And you can certainly come up with things, but this is what I came up with thinking about it and looking at a lot of other people's definitions of it. It's a broad area of study, and the basic purpose of it is to enable computers to do things that at some point we thought of as requiring human intelligence. And so that's an important part of it, is that like previously or at some point required human intelligence. And so what we'll find with AI is that it is a broad moving target. So once something is widespread and adopted, and even if it was previously AI research, it's kind of not considered AI anymore once it's commonplace. It moves out of that umbrella of AI. Looking at artificial intelligence areas, so these are just some of the broader areas that you might find in AI. So problem solving and reasoning. So anything about making decisions or satisfying constraints. So this can be something as simple as doing some kind of risk management based on different probabilities and what's going on in an environment. It can be something like satisfying constraints. So a classic example of this is if you have like a map, say of the United States, and you want to color the states, but you don't want any states that are touching each other to have the same color. It's a map coloring problem. That falls in the realm of AI, something as simple as that. Something like trying to place cell phone towers optimally, right? So that you don't have any dead spots and so you minimize cost. Optimization problems fall into the area of AI. A big area of AI that was kind of whenever AI took off as a discipline, as a subfield of computer science, was the idea of symbolic reasoning. So humans, we operate typically in natural language. We can write that language. We have symbols, basically. So we have words that mean things. We have objects and verbs and nouns and kind of all these different parts. And so the idea being that we could write software that would reason about the world in terms of symbols, so represent knowledge in that way and manipulate it. We've moved away from that. So since machine learning has become kind of very powerful, there's less and less focus on symbolic representations and just pure reasoning about things. We've moved to a more statistical model, but it's not completely gone. And it'll probably be back at some point. Another big part of AI is planning. So setting goals, pursuing goals, navigating is a big one if you're some kind of physical agent in an environment. So just planning how do you get from A to B and avoid obstacles. Learning, which is where machine learning falls. So machine learning falls under the broader term of AI. And this is all about finding patterns in data, classifying things, so looking at past examples of how something has happened and then taking a new example that you've never seen before and deciding, where it falls, making predictions about things. Also part of AI is just perception, things that we as humans would consider perception. So natural language processing, understanding, what a sentence means when you read it, and being able to respond to that, and things like computer vision and speech recognition. So taking signals out of the world and translating them into text. All of that falls into AI. So it can sometimes be hard to find examples that are not machine learning based today. So like pretty much all of the current research and I guess kind of like the cutting edge, cool, interesting stuff does incorporate some machine learning. So search is a non-machine learning example of AI, so just traditional search and optimization. So for example, a lot of games, AI players in games work this way. And so like playing chess against an AI, right? The AI is basically looking at every possible state in the future and making some utility evaluation on that. And choosing its next move. Expert systems, these are kind of like rule-based systems to help people make decisions. So we see these in the medical field sometimes. We see them sometimes just in like factories and automation systems where they're handcrafted rules, but the system will evaluate them in real time to make a decision. So early search engines definitely were kind of this traditional AI. Now we incorporate a lot of machine learning into our search engines. And basic conversational agents can be done without any machine learning. And so we'll look at an example of that on this next slide. So the example we'll look at is this program called ELIZA. And it was developed in the mid-60s. Has anybody heard of ELIZA? Okay. So the idea behind ELIZA is it's a really basic chatbot. It doesn't use any kind of machine learning or anything. It has a basic set of scripts and that it kind of feeds back to you and uses to have a conversation. And the guy who created it was mimicking a style of psychotherapy because when he was examining kind of the back and forth between the therapist and the client, it turned out that it was rather simple on the part of what the therapist was saying. And so he developed ELIZA, which is this chatbot, and it kind of took him by surprise that a lot of people, when they interacted with this software, thought they were talking to an actual person. So ELIZA is still around, and I found a JavaScript version of it. And so I went ahead and had a conversation with it earlier today and just captured that for you. So it's ELIZA, what's bothering you? And I said, I'm feeling sad. And then she says, I'm sure it's not pleasant to be sad. I say it's not. She says, please go on. And so you'll see kind of, what is it? Yes, so I don't feel very well lately. She says, that's quite interesting. And I said, yes. She says, I understand. Ask her if she can help. And she says, what are you feeling now? So the strategy she kind of uses is there are certain things that she can address directly, but most things she's just kind of generic. So I'm tired. I am whatever. How long have you been? Whatever. Kind of fill in the blank there. And then she says, I'm not sure I understand you fully. If you say that you're sorry, she does kind of have like a, that's not necessary. And then I believe that at this point I start to mess with her a little bit. She doesn't like you to talk about her, obviously. So I started to do that. And then she says this weird thing about fantasies. So I go ahead and challenge, are you real? What if I were real? Yeah. So, I don't know. Why don't you know? This can go on for a while. So, and so, she doesn't like negativity. So then I just decided to see what would happen if I put, smiley face in. And then I think I just ended it here. But so I encourage you to go take a look at this. So you can look at the code. It's not very much code at all, honestly. She does know about greetings. Saying goodbye. So this kind of, for us, we've interacted with chatbots, right? So we've seen all kinds of crazy things, and we've had the benefit of machine learning chatbots that, learn how to be Nazis on the internet and stuff, and then talk to us about it. Eliza didn't do that, but for people in the '60s, this was kind of, crazy. This was impressive, and people were tricked by this. So that was interesting, and that's probably the most interesting example I could give you of kind of social HCI and just generic AI without machine learning. But lately, it's all about machine learning. So we constantly hear about machine learning. To give you an idea of just kind of the basic example of what machine learning is, and I should say I've got a lot of sources linked in this presentation, so there's a lot of good resources out there for this. But just boiling it down, machine learning is you're feeding data to some algorithm, and it's going to build its own logic. The idea is that we're not writing custom algorithms for each problem. We're looking at data, and then the algorithm is going to develop a way of applying logic to new data. And so we'll talk about it in a little bit of detail. So there are kind of these three major areas of machine learning. There's supervised learning, and so that's where we take a machine learning algorithm and we basically give it a bunch of examples. And we'll look at this, but we take whatever it's supposed to evaluate. So for example, say that we want it to evaluate like handwritten letters, and we'll just say, just to be easy, like numbers, 1 through 9 and 0, okay? So we want it to identify digits. So we'd give it a bunch of examples of what a 0 looks like, a bunch of examples of what a 1 looks like, for each one. We would train it on that data, and then we would write a new example and see if it correctly categorized it. That's supervised learning. The big bottleneck there is obviously you have to have correctly labeled data sets for these algorithms to work. Unsupervised learning, on the other hand, is looking for structure in just kind of data that is free-form existing in the world that's not labeled. And an example of this is like if you go to the grocery store and you use like a Kroger card or any kind of membership card, or even just your credit card, they'll pay and get that data later. What they'll do is they kind of amass a list of all the things that you bought. And then we can go through that data and we can find correlations, right? So people who bought potato chips also bought beer. Well, now we know that we should put beer next to potato chips maybe in the store. Or maybe we should put them further away so that you have to go through more things and maybe you'll pick something else up. So there are a lot of examples with that kind of data in the retail world. Reinforcement learning is kind of its own thing out here. Reinforcement learning can happen for sure without a physical agent, without a robot or anything. But it's really cool to think about it in terms of robots and in terms of things that can move around in their environment. So the idea here is that you set up a state space. So if you imagine a physical agent, that might just be like the environment you're in, like a room, right? And you're going to give the agent that's exploring this state space a reward when they reach a certain place. So maybe like if I had a robot in this room and I wanted to teach it how to leave the room to find the door, I would reward it when it got to the door. and then I would reset it somewhere random in the room, let it try to find its way there, reward it when it gets there. And that reward would back propagate through the state space until it learned an optimal way to get to the door given any place it could be in this room. Reinforcement learning is really powerful, but state spaces can get very large very quickly, and that can be hard to process and keep in memory. So that's kind of the bottleneck there. There are some ways around that. So I have another example. This is Google's teachable machine. I don't know if anybody has done this, but I went ahead and did this for you and screen recorded it. So this is going to show you an example of classification. So we want to classify things into bins of some kind. We have some input and we want to classify it into some discrete output. So like in the example of handwritten digits, we want to put all the zeros in one bin, all the ones in one bin. So this is a little more fun than that. So what it will do, this is in your browser, you can do this, that's me. And you're going to just hold train. So I've tilted my head that way, and so I'm telling it when my head's that way, I want the cat. When my head is straight, I'm going to train it for the purple, which is this little guy. And then my head's the other way, I'm going to train it on the third input. And so now you'll see that it's classifying me, right? As I turn my head, automatically. And then, of course, I'm trying to mess with it by leaving. So in this case, the input here is just my webcam, right? You could also use the microphone or a few other things on this example. And the output in this case is just a random GIF, but you can do sound and speech, which is really annoying, by the way. But this is a generic algorithm that's learning this input, okay? So I just happened to tilt my head, different ways to do this. I could have, like held up a sign or waved at it or put something else in the frame, and it would have learned that. So the algorithm is just analyzing what's in this frame, mapping it to these bins, and it's just learning that whenever I'm holding this button. And this actually all runs locally in your web browser. So this kind of training can be done without a ton of computation. This is something that's didn't used to be that way, but now we can do that, and so that's pretty interesting. So I'm going to kind of try to give you just a high-level, quick machine learning primer. There is a series of articles called "Machine Learning is Fun," and they're really good. So they will take you from absolutely no knowledge about machine learning, pretty much to kind of the state of the art if you read through them. They're not that long, and they're pretty interesting. So we talked about classification, and that's a big part of machine learning. So in this case, here's an example, handwritten digits. You want to classify them into bins, maybe emails, and you want to say spam or not spam, right? Another way of doing this is what's considered a neural network. This is a different structure that we use. So in this case, we're, like say we want to buy a house, right? Or we want to sell a house. And we want to decide how much we should price it for. So we can take a bunch of other homes that have sold, in our area, and we can take different attributes. So in this case, we just have 3 different attributes. We took how many bedrooms, square feet, and then a neighborhood. And so these can be discrete things. They can be continuous things. We have an input for each, and then each node is connected fully to all of these other nodes. Okay. And then we have a function inside of these nodes that we won't go into, but it's not too difficult. And essentially, when we take an example, we propagate it through this network. So we just do some math on these numbers to get weights at each of these nodes, and we'll train it on a bunch of examples, and we'll end up with certain weights here. Okay? And these weights will inform what the final price estimate is in this case. And so in this case, the output is a real number. The output could be a classification. It could be anything, really. And so we'll propagate all this through. We'll have our trained network, and then we'll put a new example in, like the house we want to sell, and we'll get out a price estimate. And we can do that over and over and over. So you may have heard about deep learning, because people will shut up about it. But what is deep learning really? It's really unimpressive. The way that it got this marketing hype and people talked about it like it was this great new thing, but it turns out all deep learning is just this, but with another layer of these, maybe a few more layers of these, okay? So we're basically making this network more and more complicated because all of these inner layers will be fully connected to each other. And so you might wind up with something like this, right? You have like all of these layers, tons of nodes, okay? And the reason that this has become a big thing is because now we have the computational power to do this. When neural networks were first imagined, long ago, certainly people thought about these, multi-layer networks, but they didn't have the power to really run them. And now we've done a lot of optimization work, and we can do that. So this is at its core what deep learning is. It is just a bigger network. It represents more things. What's also kind of interesting is these networks don't necessarily take into account just a basic neural network, the state of the world. So it kind of looks at each input as an independent training example. What we can do is we can add something about the state of the world. And this is useful for doing things like generating text. So I could train this on a corpus of books, and then I could give it a word, and it could give me what the next word should be, and the next word, and the next word, and kind of predict that and generate something. This becomes really useful in things like language translation. So the idea here is that we can encode basically something in one language, and because it's language, it has the state. The state is meaningful, right? Sentences come in a particular order, and that may vary by language, right? You may not always go noun, verb, or something like that. This can change, okay? But you'll put it through this network, you're going to get out these encoded values, and then what you can do is you can use a different network trained on a different language to decode these values. So these values have no language. And so this is how we do, this is how Google Translate works now. Turns out to be really effective. And so you can essentially take any language and put it out to any other language. It's not perfect, obviously, but it does a really good job. So you can also do this with kind of just anything, it turns out. So Google did some interesting studies where they did like a help desk kind of chat bot just to solve arbitrary problems of Google employees, and using this same setup and just taking the encoded state and trying to decode it into what the support response would be. And it's pretty impressive what they've been able to do. Okay, so now we're going to move on to the really fun stuff. So we have this huge title here, Deep Convolutional Generative Adversarial Networks. That sounds like a lot. It's really not that crazy, though. So what we can do is say that we want to learn, we have like an image of a piece of currency, right? And we want to know if it's fake or legitimate currency. So we could train a network on that, right? Give it a bunch of examples of this is, legitimate, real currency, and this is fake money. It's not of any value. But we can also, once we've trained that network, do the opposite of that. We can ask that network to give us a representation of what real money looks like, okay? And at first, it may not give us a very good example. But what we can do is we can pit these two machine learning algorithms against each other, okay? And we can make one a little bit better at detecting things, which will push this one to be a little bit better at generating things. And then we can do that over and over and over until we have this algorithm and this network that can generate kind of arbitrary images of legitimate currency in this case. And some of the fun modern examples of this, so this is a website called thispersondoesnotexist.com. Just go there and just refresh. You will get a unique person that does not exist over and over and over. Likewise, thiscatdoesnotexist.com. There are a lot of these. encourage you to go there and just refresh. You will, every now and then you will see something weird happen, which is always exciting. But the idea is that we've trained these networks to recognize these things, and now they can generate these things for us, and that becomes really interesting. So we should talk a little bit about machine learning performance. What matters when we're evaluating machine learning? So let's think about the case where we're doing a test for something. We're diagnosing, we're trying to screen for something. In this case, this example is dyslexia. And so we're going to run a test on someone, and we want to be able to tell them with some accuracy, some confidence, if we think they're affected by dyslexia or not. Okay? So there are a few possibilities here. So it could be the case the person is dyslexic, and we actually detect that they are dyslexic. So that's what we would call true positive. It could be the case that they're dyslexic, but we fail to detect it. So that would be a false negative. They walk out thinking they're not dyslexic, but they are. On the other hand, the person could be non-dyslexic, and we could still tell them that they are. So that would be a false positive. Or they could be non-dyslexic, and we could rightfully tell them that they're non-dyslexic, which is a true negative. Okay? So when you hear about the performance of an algorithm, it's important that you think about all of these things. Because just because we're really good at getting, one of these boxes doesn't mean that we're really good at all of these boxes. And that matters depending on what the application is. So these are some common metrics that are used in machine learning, specifically precision recall, sensitivity, specificity. And they all have to do with how these stack up against each other. So I'll give you some real examples here. So Tesla's autopilot feature, what it does, because of the sensors that it has, is that highway signs are things that you would not want the car to stop for, right? They're fixed obstacles that are not going to interfere with the car driving if the radar detects them. So we don't want to falsely detect them as an obstacle that requires us to stop. Okay? And when we're thinking about this, think about signs like mounted overhead when you're driving down a freeway. And so what happens with the radar sensors when you're far away, obviously that doesn't appear overhead necessarily, but they're fixed, they're not moving. Similar thing like people, debris or like a hubcap or a tire or something is on the road, right? And so we don't want the car to stop if it's not in its path and it's, an obstacle that shouldn't be there. So in order to counter this, what we do is we filter out anything that's not moving. We just assume that that's safe. This has caused a lot of problems for Tesla in terms of crashes. So there have been a number of times where Tesla vehicles have crashed into like large 18-wheelers that are pulling across a street because they perceive them as stopped objects when they shouldn't. So this is a case when it really matters, like a false negative. So let's see if. Okay, so there's another thing we should talk about quickly in terms of machine learning performance. So we talked about getting the class right, like if we're trying to sort things. But if we're trying to fit, like say, the housing prices or something, we've basically got all these data points out here, and we're trying to fit a curve to it. If we're talking about 2 dimensions, and I should say machine learning is usually way more than 2 dimensions, so you can't visualize it like this, but if you could. Here is what we would call an underfit. So we've just kind of done our best here to put a line there, but it's not great. Like we could do a better job. We could use a polynomial function, and we could pretty much do a good job of mapping this. On the other hand, if we overtrain our network on examples that are very specific, we can get this function that hits every one of these examples, but it's going to be horrible when we give it something new. So where you want to be is in the middle. You want to avoid these two sides. So thinking about this, not all errors have the same real-world cost. So think about these differing domains. So what is the cost of accidentally detecting Hey Siri when you didn't have a Hey Siri? Might not be awful. But then when we think about something like detecting a pedestrian in the middle of the road when our car is driving itself, that matters a lot more. Or when we think about using facial recognition to convict someone of a crime, that probably matters a lot too in terms of the algorithm being accurate. So here's another example. So probably read about Uber hitting a pedestrian, killing a pedestrian in Arizona. And so what happened here is that Uber's vehicle was running its autonomous software. Okay, the car they were using had its own automatic braking system that came with the car, not Uber's system. And it was a very basic system that just, if something came into the path of the vehicle, it slams on the brakes. It's a common assistive package, okay? But Uber had decided to disable that. And the reason they disabled that is they didn't want false positives to interrupt their training of their system. So when they encountered this pedestrian, Uber's system, first of all, identified it as an unknown object, then it thought it was a vehicle, then it thought it was a bicycle. And the car's automatic stopping system activated in time to avoid the pedestrian. But Uber disregarded it and hit the pedestrian anyways. And so their focus was on false positives here. They were trying to eliminate the false positives. But in this case, that ended up being a pretty bad decision for them. So summing up kind of the machine learning basics, this is the XKCD. And basically, the idea is that all machine learning is throwing a bunch of linear algebra and statistics at big piles of data and trying to get meaning out of it. And that's not too far from the truth. And we'll talk about kind of the implications that come with that. So let's get to HCI and machine learning and AI. So where do they fit together? So kind of one of the biggest things that machine learning and AI can do for HCI is provide new methods of input. That's a big one. So things like recognizing a person's face or their voice or their gestures or their touch input. Machine learning algorithms are used to do that accurately. And it can be used to personalize things per user. So one of the interesting things to do, so like targeting on a touch screen. So most of the targets you hit like on your phone are much smaller than your finger that actually hits them. And it turns out that some people have different ways of targeting things. So older people target different than younger people. People who have certain disabilities target differently than people that do not have those disabilities. So machine learning algorithm can really improve usability and user experience because it can learn that on a per user basis and make adjustments for that kind of thing. Another thing we can do is learn from the experiences of one user or a bunch of users and use that to benefit a new user. So a lot of services like Netflix or Apple Music or whatever, when you first join, will say like, pick a few artists you like or pick a few movies you like. And what they do is they use that and then they find a bunch of similar people who like those things and use that to kind of bootstrap the process of giving you recommendations when you haven't used their service for anything yet. So that's kind of some of the most basic things. And I should say this is not easy. It can be very difficult to evaluate. And so there are a lot of challenges here. And particularly when we present data or interfaces driven by machine learning or AI algorithms to a user, and when those algorithms are wrong or confused, that's a real HCI challenge. So that's a lot of what we'll talk about. So just some more examples of HCI and AI input. So things like speech and vision, gestures, things like the IMUs, so like the motion of a device, like your phone, or a good example from like the gaming world is like the Wii controller was kind of a big interesting input device, which is just using the position of that device over time as an input device. There's a whole field of kind of related directly to HCI called affective computing, and that's all about trying to figure out how a user's emotional state while they're using a system, and then using that to improve things for them or to make the system easier to use. So talking about personalization, a big thing we can do is model a user's behavior. This is really useful for testing, it turns out. So like one thing we can do for like planes, like pilots who are flying airplanes, we can observe them flying in a simulator for a while. We can build an AI model of what they would do in any given situation, and then we can run a bunch of simulations to see how they would behave and possibly identify situations that are problematic before they happen. So things like adapting interfaces, speech recognition is a huge one. So most speech recognition systems we use, they do learn over time about our accents, our inflections, how our voice sounds in comparison to kind of the base model, and they adapt to that. A lot of the wake words, like at least on your phones or your personal devices, they are customized to your voice so that when some random person says, "Hey Siri," hopefully your phone doesn't respond unless it's you. We'll talk about these kind of interfaces, but kind of the idea of knowing things about a user. So like in a case of a mobile device, knowing where a user's home is, where their work is, learning these things about them to be proactive and to assist them. Obviously recommending things, so that's pretty big. Any kind of like shopping or anything where you're consuming content or creating things for a new user. Adapting behavior. So this is a big part of anticipatory design. So like the Nest thermostat, for example, the idea is that after just a short time of using it, it's going to automatically take care of setting the temperature in your home, and you're never going to have to think about it. And it's doing that by learning a lot about your behaviors early on, and then making decisions for you and anticipating things. So a big thing about like the Nest thermostat is that it tends to kind of know when you're going to come home. So it will, like if it's hot outside, it will start your house cooling down, an hour before you get there, so that when you get there, it's actually at the temperature you like. So it's anticipating your arrival. And then obviously understanding user behavior just through analytics, and that's useful for things like advertising and targeting people. So here's some examples. And I would encourage you to so Netflix is pretty good. They have a good tech blog that shows a lot of the things they do with machine learning and HCI. So this is an example. Netflix actually does a lot with thumbnail generation. And one of the things they need to do, I should say this article that this comes from also includes, they have algorithms that actually automatically make these thumbnails for them. And so they can do things like pick out the person in the scene and what's the most salient thing and what are the colors that matter here and where should we put the logo and where should we put new episodes and where does all that go. But in this case, Netflix is trying to compare the performance of these thumbnails, but across different localizations, so different countries, so you see different languages here for the same show. And so they've got to be able to find the same thumbnails and compare them. And it turns out that this is somewhat difficult too because of the nature of film, that things are color corrected and color graded in different ways from other just photos that we train on. And so they have to make some changes for that. That's one kind of general example. This isn't catered to any specific user. This is for Netflix to get an idea of how well one of their other algorithms is performing. Now, talking about specific users, Netflix will actually make you a custom thumbnail for each thing that they're presenting to you based on things that you've watched previously. So in this case, if you tended to like films with Matt Damon in them, and it has a some title you haven't watched and it has Matt Damon, it should put him in the thumbnail, right? Because that's probably will get you to click on it, and maybe convince you to watch it. So this is an example they provide of all of these different things that they've generated for the same title here, and it's user dependent. Surprisingly, I should say, Airbnb does a lot of interesting work just in UI design and dealing with engineering and AI and machine learning. They have some pretty good blogs where they detail a lot of what they do. But this is just one of the features that they've kind of put an in-depth series on. It's what Airbnb calls smart pricing. And the idea is that people who are, putting their home or a place that they own on Airbnb, they want to price it in a way that makes sense, right? And so it turns out that pricing depends on a lot of factors. Depends on what's going on in the location you're at. It can depend on really specific things. So like Airbnb's first algorithm kind of did like this point thing and just expanded outward to do pricing. But it turns out that in some cities, being just across a river makes a huge difference, right? And there's a huge pricing disparity that happens there. And so they kind of dynamically generate these micro neighborhoods and clusters, and these change over time. And so if you go read some of these blogs, they've done a really good job of talking about how they've developed their algorithm over time. And the purpose of this is for the users who are hosting people on Airbnb, is to allow them to price things in a way that makes sense. They also found that they did have to give some controls to users, so they wanted to be able to fix minimums and maximums and have some input to this, and not just have an algorithm that was running without their knowledge. Here's like a temporal example. So this is in Austin. This is South by Southwest. So you can see when that happens, that event every year. Spike in people wanting to stay places, and so pricing goes up, obviously. And so it can be important what time scale you look at this over too, because this is like an annual event, which turns out to be pretty meaningful in this business. So talking about anticipatory design, we talked about the Nest thermostat, but here are some other examples. So on the Uber app, for example, if you use the Uber app and you take an Uber somewhere, and then you stay there for however long, and then you open the Uber app back up while you're within that general area, one of the options it's going to give you is a return option. Because it's pretty reasonable to expect that if you've traveled somewhere, you want to travel back, probably. And so you're anticipating the user's need. So this would not be there if that were not the situation. So we see this with predictive text. So more recently, Gmail has put this into kind of just composing emails. Sometimes it works really well. Sometimes it does interesting things. So another big part of HCI and AI together is understanding context, which helps us understand a user's intention, which does change with context. So you'll see a lot of research into this. And this can even be, things like the way that we inflect our speech when we're speaking to different people, or when we're at home, or when we're in a professional environment. These things change. But the idea being that if we can understand these things using machine learning, using the perception that we have, we can increase the common ground that we have with the user and create a better experience. And so we also have this idea of ambient intelligence, and that's basically trying to get the information the user needs to them either just in time or a little bit ahead of time. So sometimes I know if I get in my car and I pick up my phone, it will say 14 minutes to Mississippi State. Okay, it's anticipating where I'm going. It's usually right, and it's trying to give me some information about that. So we'll talk about a few. Kind of want to just talk about AI designing interfaces, right? Is that a thing? Is that happening? Will we not have a job, designing interfaces eventually because the AI should just do this for us? And so this is a really interesting website. It's algorithms.design, because that's a domain now. And it's got a lot of really good examples. So I really encourage you to go look at it. I'm just going to hit on a few of them. So here's one big idea with using machine learning and UI design. And this is the idea of evolutionary design or genetic algorithms. And so the idea is that we would take kind of this sketch or this prototype that someone makes in a tool, and we would generate different mutations of it. Thinking about this like we think about genetics, right? We would maybe change, like rounded corners, different hues maybe, and we would pick out some distinct ones, and then we might present, 20 of those to the designer. And then they would choose, which ones they liked the most. Then we would do another round of genetic computation on that until we converge at something. And this can be really interesting. But you've got to think about the different dimensions that you act on. So this is actually an open source one. You can go to GitHub and look at this. I think it's for the Sketch program, but it will generate on different characteristics of a sketched UI and kind of give you these options. One interesting example of this in actual product design is the idea of kind of exploring a parameter space, not just for UIs, but for physical products. In this case, Autodesk worked with Airbus to create this, this is a partition in a plane, and they used genetic algorithms or evolutionary algorithms to explore the space of how they could design this, and essentially let the machine learning algorithm optimize for weight and stability and strength here, and they end up with this kind of odd-looking design that no human designer probably would have come up with, but turns out to be really optimal in terms of it doesn't weigh nearly as much as the thing we would have created, and is much stronger than the thing we would have created. So we see this in applications like this. We also see this for designing things like UAV or drones. Kind of the frames on those, they need to be light, they need to be pretty robust, and we can let an algorithm make those design choices for us and optimize for us. So there are some challenges that come along with this. And so early on, when people started to consider machine learning and HCI and how all of that comes together, the big debate, I guess in the kind of the late 90s, was this idea of direct manipulation versus agents. So how much do you want to, give a computer a high-level task and trust it to go off and do that for you, versus do you want to directly manipulate the parameters of what it's doing? And there's a trade-off here. And there were two camps, and they argued a lot, and they probably still argue a lot. But kind of what we arrived at, no surprise, is a compromise between the two, where you try you can hide things that you can do really well usually, but you need to allow some adjustment usually on a few things, or things that you're not as good at. A huge area of AI and machine learning is being able to explain why your machine learning algorithm made the decision that it made. This turns out to be very difficult to do in most cases because of the way the algorithms work, because of the way that they're trained. Explaining why a system did something is not always simple. And this can be really important. If you think about something like automation on a factory line, you need to know why it did something that wasn't safe. What did it sense? What confused it? What was the edge case? And if you can't get that information, people aren't going to be comfortable using these systems in high-risk scenarios. So that's a trade-off. Also, users get frustrated. So there's actually a pretty good paper that I recently read where they went and they mined all of the reviews on, I think, Facebook, Netflix, Google Maps, all on the Google Play Store, and they narrowed it down to people complaining about things that were the AI algorithms generating content and making decisions that were confusing for the users. And it was really interesting to see that there were enough people that were complaining about things that turn out to be nuances of these algorithms that are not making themselves apparent to users. These users don't understand that an algorithm is making a mistake or it's doing something that's causing them to have a bad experience. So we also, this is kind of in line with the direct versus the agents. talking about AI versus IA. IA being this idea of augmenting a human intelligence rather than just doing everything like a human would do or taking over for them. And you can think of this as kind of like you've got, on one hand, an autonomous driverless vehicle, right? You're just going to sit in it. It's going to take you wherever you want to go. And on the other hand, you've got vehicles that have things like a feature that will not let you pull into a lane and hit another car, or that will apply the brakes for you before you rear end someone. These are augmenting your abilities. You're still very much in the loop and in control of the vehicle, but these things are assisting you rather than completely taking over. So definitely the biggest issue and the biggest concern for HCI that you'll see if you start to look at research and companies that deal with HCI and machine learning together is this idea of uncertainty. And so with a machine learning algorithm, there's always a chance that we get the wrong result. We classify something wrong, we give back something that's not correct for the circumstance. And as a HCI, as someone who's interested in the experience the user's having, you've got a plan for that. And in some cases, you want to be able to explain that. But in other cases, you need to be sure that when that wrong result comes back, it doesn't put your user in a state of total confusion. You've got to consider that wrong result or that odd result as an error, as a failure, and you've got to fail gracefully, just like you would with anything else. Just like if a network connection disappeared or a battery level got low, you need to have a way of dealing with it. One of the ways that we deal with this a lot is in an interface. We might have like an area that's context sensitive. So if you've got like, I don't know, text selected in your presentation material, maybe it's got like the font color or the font choices in a menu. If you have a graphic selected, it's got like, reflection and opacity or something. And we can use machine learning to drive what features we present first to the user to try to optimize. But we know that that area is just for that context-sensitive part of the interface. And of course, the user has another way to do everything they want to do. But they know that certain areas are context-related and certain areas are kind of always there to fall back on. Another big area of machine learning is it can help you organize menus in software that has a lot of menu options. It turns out there's a lot of ways to organize it. And you can use machine learning to optimize that. But essentially, the biggest concerns are designing for these unexpected outputs and explaining these outputs. Kind of what a recent example from Google, they were looking at the effects of different ways of explaining to a user that they were misclassifying the thing that they were drawing. So in some cases, they would say like, I didn't recognize this as what I asked you to draw, and these are examples of how positive examples of what I think that looks like. And then in the other case, they were saying like, the thing you drew looks like these things, not the thing I asked for. And it turns out people don't like this so much. They don't like being told this way. So it really matters how you present this to a user. Just some things to think about. These are both good and bad AI. So pretty much every example of good AI is also an example of bad AI if you stare at it long enough. And we'll talk about this a little bit more when we talk about ethics and HCI. But all of these can be good and bad things. So here are some really great resources that you can look at if you're interested in this more. And that's all I have for us today. On Thursday, we will do robots and VR and AR and all of these things. And that will be our last class.